So here you see that in the example 4.73, recycle and purge in the synthesis of methanol. So first of all we have to solve this problem. So the problem question is the methanol is produced in the reaction of carbon dioxide and hydrogen. We see that in the reactant carbon dioxide and hydrogen, and the product is methanol and H2O water. So also mention that the fresh feed to the process contains hydrogen, carbon dioxide, and 0.4 more percent inerts. The reactor effluent passes to a condenser, uh, then that removes essentially all of the methanol and water formed, and none of the reactants or inerts. Okay, the latter substances are recycled to the reactor to avoid build-up in the inerts in the system. A part system is withdrawn from the recycle. The feed to the reactor composition is this, and the single pass combustion of hydrogen is 60%. So we have to calculate the molar flow rates of molar and molar composition of the fresh feed, and the total feed to the reactor, recycle stream and parts stream, and methanol production rate 155 kilomole methanol per hour. So there's a lot of information in this question. So for the simplification, we have to first of all draw the flow chart. By this we can easily understand this question. So first let's move one by one. First of all we have a reactor. Okay, in this reactor the feed is carbon dioxide and hydrogen and inerts. So first let me draw the reactor. So this is the reactor. Okay, so there is a reactor input, there must be a reactor input and reactor output of products. Okay, then you see that in the question the reactor effluent passes to a condenser, so there might be a condenser. So this is the condenser. Remove essentially all of the methanol and water form, and none of the reactor inerts. The latter substance, we see that the latter substance recycled to the reactor. So this is the product we collect, and some of this, some the latter substance is recycled. So some of this is recycled. So this will be the recycle stream. Okay, and then to avoid buildup of inner system, the pass stream. So there is also a pass stream is withdrawn from the recycle, which remove the inner material. So there is also a pass streams here. Okay, so now here else mentioned that the feed to the reactor, not the fresh feed to the process. This is the fresh feed to the process, and this is the feed to the reactor. So here given that the feed to the reactor, that means this composition. So I have to write it down, so that the feed reactor to the process, and the feed to the reactor, not the process, contains 28 mole percent. We see that 28 mole percent carbon dioxide. So this will be 0 point in fraction 0.082 mole carbon dioxide, and 0.7 mole hydrogen per mole, and there is also mentioned that 2% inert, that means 0.02 mole inert per mole. Okay, so this is the feed to the reactor. And the reaction is already mentioned in the question. The reaction is carbon dioxide plus 3 hydrogen produce methanol plus water. Okay, so the product is steam. We can assume that and 1 mole carbon dioxide and 2 mole the unreacted carbon dioxide, hydrogen, and the anti-mole product is methanol. Okay, then N4 mole water, and the unreacted inerts, 2 mole inerts when we assume the basis is 100 mole fit to the reactor. Okay, so we just identify the two uh, streamline. One is fit to the reactor and other is the product of the reactor. So there is also some streamlines here, so you have to identify these streamlines. So here the question mentioned that passes through the condenser that removes essentially all of the methanol and water formed and none of the reactants of inerts. So our product will be only just N3 mole, which just produced in the reactor is the output from the condenser, and 3 mole CH3OS and N4 mole S2. So this is the our product stream, and there is no inert in this stream. And the other side, and the reaction recycle stream, there is must be carbon dioxide, hydrogen and inert stream. So first let me just think, assume that n5 mole recycled, so n5 mole out from the condenser. So the stream will be x5c mole carbon dioxide, x5 mole hydrogen per mole, carbon dioxide per mole, and inert. So inert will be 1 minus Sc minus Sh inert mole per mole. And here is, so you see that there is also a purge streams. So in this point we say this is the separation point. So the molar composition of the component carbon dioxide, hydrogen and inert, it will be same in this tree section, 3 streamline, but the total mole is different. So let me assume that the purged is stream moles, total mole is np. So the molar composition is same to the before, x5 sh hydrogen and 1 minus Sc minus sh xh per mole of inerts. And the recycle stream will be nr. Assume that nr, the composition is also same, and CH mole carbon dioxide per mole, sh mole hydrogen per mole, and 1 minus Sc minus sh mole inert per mole, which is also combined into this point. That this is the mixing point, and this is the separation point. Okay, in this mixing point there is also a fit to the process. So let's assume the fit to the process is n naught mole, and the composition of carbon dioxide, hydrogen, it will be xo carbon dioxide xo carbon dioxide, xo mole carbon dioxide per mole, and 0.996 minus, because in this question here is saying that the inerts fit to the process is 2%. So here is the written that 0.4 more percent inerts into the fluid. So this will be 0.004 mole inert per mole. So there others will be hydrogen, so 0.0996 minus x mole hydrogen per mole. So this is our main flow chart of this process. We see that this is a large process. First of all, there is a process fit. We see that there is a process fit which into the process, and there is also a recycle stream combined to the fit to the process, and is also fit to the reactor. And then the reactor product gets fit to the condenser, and the condenser removes all of the methanol and H2O from the process, and the other is recycling to the process into the reactor. and for remove the inert materials there is also a parse streams. So there is a lot of variable and a lot of operation unit. There's a lot of mixing point, separation point, has condenser and reactor. So first of all, we have to identify that from which unit or which point we begin our calculation. So for this we have to calculate the degrees of, first of all, degrees of freedom. So if you see that we have also an extra information which is 60 and the conversion. I think there is a given the conversion of hydrogen, there is written the 60% conversion of hydrogen. Yes, okay, so that's it. 60% conversion of hydrogen is given, which is an extra information is given into the question. So first of all, we have to analyze the degrees of freedom. So in the reactor we see that there is unknown is n1, n2, n3, n4, four unknowns. We can atomic balance carbon, oxygen, hydrogen, and also inert is, we see that inert it already balanced, so we can't inert balance in there. And also extra information is 60% hydrogen conversion. So there is four unknown and three atomic balance and one extra information. By this we can say that degree of freedom is equal to 0. So we have to first begin our calculation from the reactor analysis. So we see that in the reactor the reaction is carbon dioxide plus hydrogen, which will form methanol and H2O. Because of the single per 60% single per combustion, the reaction will not be completed. So that's why there will must be in the product gas the unreacted carbon dioxide and hydrogen which is out from the reactor. So first of all, from this extra information, in this extra information here is mentioned that 60% hydrogen conversion. So from this we can easily calculate. First let divide into the 3 or 4 section, which is easy to understand our solve. Okay, first of all, 60% single pass hydrogen conversion, 60% single pass hydrogen conversion, which is given in to the question. So 60% hydrogen conversion, that means the 40% is unconverted and immersed at the reactor outlet. So the we see that the reactor outlet is N2. So the our N2 will be 70 input hydrogen is 70 mole. You see that into 100 into 0.7, this will be 70 mole. So the unreacted is 0.42%, that means 0.4. So this will be 28 mole hydrogen. So now we calculate the N2 unknown. So now we just know which is, this is unreacted hydrogen. So reacted hydrogen will be reacted hydrogen 60%. So 70 into 0.6, this will be 70 into 0.6, 70 into 0.6, this will be 42 mole reacted. Now now the carbon dioxide balance, we see that in the input the carbon dioxide is had 100 into 0.28, that means 28 mole carbon dioxide. So we see that there are 42 mole hydrogen reacted into the reaction. The reaction is carbon dioxide plus 3 hydrogen, methanol, carbon dioxide plus 3 hydrogen, and the product is methanol plus H2O. So there is reacted 42 mole. In this reaction we see that 3 mole hydrogen reacted with 1 mole of carbon dioxide. So for carbon dioxide balance, The carbon dioxide reacted is 42 mole, we know that. And the for 3 mole hydrogen, 1 mole carbon dioxide reacted, that means carbon dioxide reacted 42 by 3, 42 by 3, that means 14 mole, 14 mole carbon dioxide reacted. So the unreacted, the carbon dioxide will be N1, which is outlet in the reactor. So N1 will be, input is 28 mole, output reactant 14 mole, so output will be 14 mole of carbon dioxide outlet in the reactor. Now we can also measurement identify the variable of methanol in this N3, which is here. So in this reaction, we can see that 1 mole carbon dioxide reacted, 1 mole of methanol produced. So hence 14 mole of carbon dioxide reacted. So we can easily say that 14 mole of methanol will produce. That's it. Simple. By this astrometric equation. We can also identify this by carbon balance, atomic carbon balance, hydrogen balance, or oxygen balance. It will depend on you, because there is a lot of process, so I am just trying to solve it by astrochemistry. You can also solve this by the atomic, hydrogen balance, carbon balance, and oxygen balance. The answer will be same. Yeah. So now in H2O balance, can you see that 1 mole carbon dioxide is reacted to 1 mole of H2O produced. So H2O, that means N4 will be also 14 mole H2O in the outlet in the reactor. So first of all, we also measure the four variables N1, N2, N3, and N4, which is outlet into the reactor in the reactor. So now move into the another unit, the condenser analysis. In the condenser there is no reaction is occurred, just the separation here, just the input is separated to output, just by the condensation process. So we can easily know total mole balance is apply in the condenser analysis. So now in the condenser analysis, okay, condenser analysis. We can easily total mole balance, that means N1 plus N2 plus N3 plus N4 plus 2 is equal to N5 plus N3 plus N4. So you already know that N1, N2, N4, and N5, and N3 and N4. So by this you can easily calculate the N5. N5 will be 44 mole, N5 44 mole, which is outlet from the condenser and is participated to the recycle to the process. And then we can easily calculate, hence we find out the N5, which is 44 mole total mole. So by this we can easily calculate the molar fraction of carbon dioxide, hydrogen, and inerts in this streamlines. So this will be for carbon dioxide. For carbon dioxide, this will be, we know that the carbon dioxide is total is N1, so N1 will be N5 into Xc. So we already know N1 and N5, so Xc will be N1 divided by N5, which is 0.3182 mole carbon dioxide per mole. And then hydrogen balance, so N2 is equal to Xh into N5. So by this we can easily calculate the Hc. The molar fraction of hydrogen is 0.6364 mole of hydrogen per mole. So the other inert materials mole fraction is will be 1 minus Xc minus Hs, which is equal to 0.04545 mole inert per mole. So now we already identified the Xc, Hs, and 1 minus Xc, Hs. So now we just variable is N, P, and R, and N naught, X naught, Xc. So now we can calculate for the calculation of NP, NR, and not the we should calculate the total mole balance. That means overall the process. We can overall balance. We can use overall balance, or we can use the mixing point for the further analysis. So now the flash bit recycling mixing point analysis, and this is the point, mixing point. So in this mixing point we see that there is a process, flash bit process into the flash bit into the process, and this other will be the recycle stream. In the recycle stream there is R, R, and R is unknown, and N node is also unknown. So in this mixing point, the total mole balance, mixing point, the total mole balance is, it will be N naught plus NR equal to 100 mole. Okay, and then this is one equation. There is two unknown N naught and NR, and then we can easily the inert balance in the mixing point. The inert balance will be N naught into 0.004 is equal to, is plus NR into 0.04545 is equal to 100 into 0.02, that means 2. So there is also two unknown N naught and NR. By these two equation 1 and 2 we can easily solve the N naught and NR. So N naught and NR will be, by solving these two equation, N naught is 61.4 mole flash bit, and the NR is equal to 38.6 mole recycle to the process. So we already solved, we already just solve this N naught and NR. So our problem is easy now. Just to find out the two unknowns now. One unknown, that is just XO in the molar composition of carbon dioxide, which is flash bit into the process. So for this balance in this mixing point, we just have to carbon dioxide balance, easily calculate the molar composition of carbon dioxide in for this flash bit into the process. So N naught, this will be N naught into X naught plus N naught into Xc equal to 100 into 0.28, that means 28. So there is already, we know, N naught, NR, and Xc. So the X naught is, it will be 0.256 mole carbon dioxide per mole. And then we can easily calculate the molar fraction of hydrogen. This is 0.996 minus Xc, which is equal to 0.740 mole hydrogen per mole into the flash bit process. So last of all, we have just another variable, another unknown, which is NP, the first stream molar rate, mole. So this will be overall balance. This will be just, I don't know, the overall balance. So the overall balance will be flash bit into the process, and naught is equal to N3 plus N4 plus NP. So the all are known, just NP unknown, which is equal to 4.5 mole of per stream, which is out from the process. So by this we can easily calculate the all variables which is related into this process. So that's it.